Welcome, geometry students. Today we're going to learn about geometric probability. So we're going to use lengths and areas to find geometric probability. Before we start talking about geometric probability, I just want to think about regular probability that we would think about in any situation. So think of when you go to play the lottery, for example. The probability or the chance that you would win the lottery is usually depicted as 1 in a million or 1 in 10 million, for example. So it's your odds of winning something. So to define that, probability is a measure of the likelihood of something happening. So I already mentioned the likelihood of winning the lottery, but there's also probabilities, for example, in weather. The probability of it raining, for instance, would be the chance of it raining today. The probability of it being sunny, and so forth. There's a lot of probabilities in sports as well. The likelihood that a particular sports team might win against another competitor. So probability is very prevalent in many different situations outside of the classroom. Geometric probability is just simply a ratio. Keep in mind, a ratio is just a comparison with a fraction. A ratio that involves a geometric measure. Such as length or area. So we've spent a lot of time this unit calculating different areas. So we're going to be using some of those areas to calculate probabilities. Let's start with probability dealing with lengths. So it says let AB be a segment that contains the segment CD. So here's our picture. We have segment AB, and then segment CD is a part of that original segment. If a point K is on AB and is chosen at random, then the probability that it is on CD is the ratio of the length of CD to the length of AB. So essentially what we're saying is if I put a point P anywhere on this segment AB, any point K on that segment, if we were trying to find the probability of it being on segment CD, then we would do the length of CD over the length of the whole segment AB. Now the reason why this occurs is essentially it's looking at the ratio of the size to find out what are the odds that it would fall on CD rather than another location outside of that but still on segment AB. So we're going to do the length of where we're looking for it to occur over the length of the whole segment. If you notice our notation here, P is standing for probability, and then in parentheses we put what we want to find the probability of. We're looking for K to be on segment CD. So we list it as probability of K being on CD. Let's take a look at an example. Example 1 says to use the lengths to find geometric probability. Find the probability that a point chosen at random on FJ is on GK. Okay, so we want to think about a point being chosen at random, and we want to know if it's going to fall on GK, and if so, what's the probability? So we put P for probability. It's a point, and we want to know if it's on GK. So then our formula for this essentially is the length of GK. That's where we want it to be, so that's essentially where we would get our desired outcome over the entire length. Well, it's saying that the point is going to be chosen at random, not just anywhere on this number line, but specifically on FJ. So we have the part over the total length. So now let's continue on. This probability, well, the length of GK, we notice we're counting here by 1, so we have a length of 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the total length is 12. Now, I want to comment here, if you for some reason came up with 10 over 13, you probably made a very common mistake. When I'm counting for the length of GK, for example, point G is my beginning point, so that's 0. So it's not till I make my first move that I count to 1. So you want to keep in mind you're starting on 0 and then you move 1 place all the way up to 9 over 12. If you can, you're going to simplify this. Well, 9/12 simplifies to be 3/4. So basically, I have a 3 out of 4 chance that my point chosen at random will be on segment GK. Another way that we often see these probabilities listed would be a percentage. Well, 3 over 4 is the same as 0.75, which becomes 75% by moving your decimal over 2 places. Another way you're going to see this ratio would be 3:4. So keep in mind all of these versions are the same answer but just a different format, and you should know all of them because they're all useful in different situations. So we have a 75% chance of this occurring. Okay, let's look at probability and its dealings with area. It says let J be a region that contains region M. If a point K in J is chosen at random, then the probability that it is in region M is the ratio of the area of M to the ratio of the area of J. Again, this sounds kind of complex, but we're just looking at what are the chances that K is in region M. So our point is going to be chosen at random, and the whole area is region J. So the whole area on bottom is the area of region J. And that region might be a rectangle, it might be a square, a circle, etc. So then what we need to do is find the area of the smaller region, which is the area that we're trying to find the likelihood of the point falling in. So in the numerator, we would do the area of region M. So the probability that the point K is in region M would be the area of that region divided by the area of the total region where it's possible for the point to be chosen. Again, we'll show that probability either as a percentage, a fraction, or another form of a ratio. So now we're not going to be seeing a number line. That's when we're dealing with lengths. Now we're going to see two-dimensional figures such as this. So it says a golf ball is hit and stops somewhere on the green. So it hits somewhere within this circle. A prize is won if it stops in the painted circle. So we're saying that a prize is won if it stops in this white painted circle. The diameters of the green and circle are shown. If the ball is equally likely to stop on any point on the green, what is the probability that a prize is won? Keep in mind, you're going to see this phrase a lot, equally likely, because that's just saying that there's no reason why it would fall in one spot more than another. It's an equal chance for that to occur. So we're looking for what is the probability that a prize is won. Well, we need to consider that the prize is won when it falls in the white painted circle. So area of painted circle divided by area of the green, which is the larger circle. So again, when we set up this probability, we're doing the area of the space that we want to find the likelihood of it occurring. In this case, it's the prize winning, and that only happens in the painted circle, divided by the area of the entire region. Well, we're dealing with area of a circle here, so area would be pi r squared. So in this case, we're given the diameters, and we need to find the radius. So in this case, since the diameter is 15 feet, I'm just going to cross that out and say the radius would be 7.5 feet. Likewise, 75 feet is really just a radius of 37.5 feet for the larger green. So the area of the painted would be pi times 7.5 squared divided by the area of the green, which would be pi times 37.5 squared. Now we don't need to subtract out the white space because that would still be part of the entire space. So we're doing the entire whole circle and just the smaller circle on top. So if we simplify this real quick, we can start by crossing out our pi's. Those would simplify before we even multiply. So we have 7.5 squared divided by 37.5. Well, that's approximately 56.25 square units divided by 1,406.25 square units. So if we were to divide that through and simplify, we're going to get 1 out of 25, which is the same as 0.04 or 4%. So there's only a 4% chance that I'm going to win the prize by falling in this small circle when compared to the entire space. So not a very good chance of that occurring. Example 3. A dartboard is shown, so a dart is thrown and hits the target shown. If the dart is equally likely to hit any point on the target, keep in mind the target includes everything inside of this square. What is the probability that it is outside the circle but inside the larger square? So if we're talking about outside of the circle, here's our circle, but still inside the larger square, we're looking for the probability of the point chosen or the dart hitting one of these 4 regions. So we have to think about how we've calculated areas of shaded regions in the past. So we're looking for the probability that the dart hits in larger square, but outside of the circle. You might be wondering, do I really have to write that out? Yes, sometimes it's pretty simple to write out what you're finding the probability of. Other times, like in this case, you need to have more details since there are 2 requirements, so you do need to include all of that. You can make it as simple as possible as long as you're putting everything that's required. So the probability of this occurring, we want to do the area of the entire square as the whole. And then in order to find the area of what we're looking for, we're talking about the area of the square minus area of circle. So we're going to do the area of the larger square minus the area of the whole circle. In this case, the little yellow square on the inside is not going to be used because that's just part of the area of the circle. So you really don't need to even use that in this particular problem. Well, the area of the square, since it's a square, it would be 18 times 18. So I'm just going to go over here and calculate the areas separately. The area of the square then is equal to 324 inches squared. We also need the area of the circle. So we're going to use pi r squared. In this case, the radius of the circle is going to be half the diameter. Well, the diameter is 18, so the radius would be 9. Which is approximately 254.47 square inches. So if we come over here and go back to our formula, the area of the square is 324, taking out the area of the circle, 324 minus the area of the circle, which is about 254.47, divided by the entire area, which again is the 324 square units for the square. So if we simplify this, we get about 69.53 over 324, which comes out to be 0.2146. So if we look at this from a percentage standpoint, since it's not a nice, neat fraction like some of the others have been, this is about a 21.5% chance of occurring. So it's larger that this would occur than it was the previous that was only a 4% chance. This is over 4 times as likely to occur. So when you're dealing with probability, a common way to show that would be to show it in a percentage form. Go ahead and try the You Try Nows and make sure you look carefully at the last example. There are some congruent measures of a length of 5. Have a good day.